Okay, well, 7:55, and I am here to help you with whatever you might have. I tested out the question in the comment spot, so I'm hoping you can ask me questions in the comment spot, but I might be wrong, and if I am, you just want to send me an email. Send me an email if you're having trouble. I've got it tested out on my iPad here. And it looks to be that I am broadcasting, so that's good. I thought maybe my questions would come up, but that's not working on my big screen, so we'll see what happens. Welcome to review time. If you have any questions, I'll be here to answer questions, and if you have no questions, that's really okay with me. I'm just going to be grading, so you can watch me grade. That's okay. Yeah, trust me. So the test is on types of reactions and reaction rates, which is found in chapter 17 of your textbook. Your textbook's got some great questions, so if you have any of those, you can ask those, or the review worksheet, or your lab questions. I got all that stuff here. See whatever you write on the screen too, so I can show you like problems in that way. And hopefully it'll work. Okay, I'm here. I'll be listening for you in your typed spots. Got my textbook now. So yeah, if nobody asks a question, I'll just go get some ice cream. Yeah, keep checking for emails. Oh, I got one. Looks like I have me as a viewer and one other. Thank you to that one other person. I'm just going to answer some emails. Contact. Nope. Put in my own text. I've got no email still, so nobody must have questions yet. That's good. Yeah. I'm going to do some computer things here. Get ready for honors hymn tomorrow. I got to put my stuff together for them, so figure why not do that? Two things at once, right? What do you do? Ooh, twist it. That's totally Google. I got your papers agreed right here. Next up is Justin and Jonathan. I'm going to grade your papers. Yeah, I don't know. Any questions? In your chat feature? Currently, I click the you can ask questions button, but I'm not sure exactly how that all works. So send me an email or type something in the comment box. I'm watching the comment box on my other thing, on my other iPad. Hopefully, yeah, there's something interesting. Equilibrium, gas rates, reactions. I got your reaction rate labs right here. I'm gonna grade them. Yep, I have 4 viewers. Hello to my viewers. If you have a question, please email me. Otherwise, here I am, grading papers. Anyway, welcome to my room. This is my office / room I sew in. It's really weird to have people watching working, but that's fine. That's fine. I have 5 viewers, but nobody's asking me any questions yet. So they're watching me grade. Who would love some ice cream? Yes, please. I'm doing a stellar duck grading. No, just a little bit. Etna, if you're watching this, I expect a question or an email. I'll give you a shout out. Etna, a shout out. There you go. It's funny to watch myself grade. Graded web. Next to the element grade is Justin and Brandon. Ooh. Oh, yeah. I got a question. I was really excited. Apparently I don't have to type it, I just answer it. Hello to my person out there. I don't know if I should name drop this person. If you want me to name drop, I will. But yes, wherever you asked a question, that's where you ask a question. I'm not sure how you did that, but that's awesome. Thank you for doing so. Actually, it wasn't a question, you just said, wow, this is where we ask questions. Thank you. Thank you to my person who sent meeting though. I keep like looking at my video here, but maybe you're right, I do have to refresh. Thank you. Thank you. I got a question. It's exciting. Oh, we do have good. A question. Okay. Shout out to Big Tom. Thanks for watching, Big Tom, and for sending me a question on however you did so. That's awesome. I do have another question. Can you go over activation energy and the differences between exothermic and endothermic in correlation to activation energy? Yes, I can. Let me put myself on a different screen here. So now I hope you can just see my screen. And when we're dealing with activation energy, that's EA. That's the amount of energy you need in order to have a reaction actually happen, like the minimum amount of energy. So we look at two different graphs, and you're looking at potential energy versus time, or course of the reaction, whichever way you want to look at it. Some graphs go this way, goes up and it gets lower. And some graphs are going the opposite, where it starts low and gets high. Now, if we take a look at this one on the left side, this one, here's our reactants, where it starts at the beginning of time, and here's our products at the end of time. Since our reactants are higher than our products, this one is an exothermic chart. This difference right here is the amount of heat that is given off during the reaction. On the opposite side, we can see we've got reactants on the left, so products on the right. And since as time goes on, we're gaining in potential energy, that means we had to increase the amount of potential energy we have. We had to add heat plus Q, adding heat. The other side is negative Q. This is the endothermic potential energy chart. Now, the most important part for tomorrow is really to look at the activation energy, because that's the newest thing. For exothermic, your activation energy is right here. It's from wherever your reactants are to the top of the hill. The top of the hill up here is called the transition state. It's hard to write, sorry. The transition state is like the mixture of reactants products. It's when they're trying to be products, but they're kind of reactants, they're halfway in between. So this difference is your activation energy for the exothermic. If we look at the endothermic, the difference goes still from the reactants all the way to the transition state, which is at the top of the hill. This blue part here is the activation energy. So if we actually put numbers to it, like let's say this starts at 10, 20, 30, 40, up here is 50. Your activation energy isn't 50. Your activation energy for this one is equal to the 50 minus the 10, which is equal to 40. Most likely it'll be in joules or kilojoules, so 40 kilojoules might be your units for that, 40. If we look at the one for exothermic, we'll put some marks on that one too. Maybe 10, 20, 30, 40, make the top 50 again. For our exothermic graph, we went from 30 to 50. So my activation energy for this one is equal to the 50 minus the 30, or in other words, 20 kilojoules. So those are the things I would know for the chart as far as activation energy goes. Okay, so my other question. The other question is about if you use Le Chatelier's principle, specifically when you look at change in temperature. Like if you increase the temperature in endothermic or exothermic reaction, how will you know which way the system shifts? Okay, that's a great question. I'm just going to write like a generic equation. A plus B makes AB. Let's say you have an exothermic reaction. In an exothermic reaction, then your products will have the heat. In an exothermic reaction, you're producing the heat. So we kind of use this idea to add heat to the equation. So once heat's in the equation, then I can kind of see what part it is, products or reactants. And then I can think about it just like in concentration. What side is too heavy? So if I have an exothermic reaction, my heat is on the product side. And let's say I take this is like a whole beaker. Inside the beaker, there's A, there's B, and there's AB stuff. So the whole beaker, I'm going to heat it up. Now when I heat it up, I'm really not just applying it to the reactant side. My heat, since this is exothermic, is really adding to this product side. So since this product side is too heavy, the reaction will shift. In other words, it'll start to go faster to the left. It'll start to make more reactants. And so the shift will be left. And if we add colors to this, like maybe this side is yellow and this side is green, however it looks when it starts, it's going to turn and look more yellow as you heat it because it's an exothermic reaction and it has shifted to the left. Well, if we've got an endothermic, say the same thing, A plus B makes AB. If I've got it inside of a bucket, and once again, we'll pick different colors. Let's say this is red and this one's blue. When I first look at this chemical equilibrium, what I've got going on, if you take a look at the arrows, I can see that the forward reaction is more prevalent. My KEQ in this case, according to the arrows, is going to be greater than 1, which means I've got a lot of AB. Now my AB is this blue stuff, and my A separated from my B is in red. But since my KEQ is greater than 1, I'm going to have a lot more ABs in the bucket. So when I look at the bucket, it's going to look really blue. Now let's say this reaction is endothermic. I'd have to tell you it's endothermic, or you have to get some data to decide that. But if it's endothermic, that means heat had to be inputted. Endo is in, heat is in. That means heat is going to act as a reactant, which means when you heat this up, it's suddenly going to add more to this side, just like a teeter totter. This side is way too heavy now. And the only way to relieve that stress is to have it shift to the right, which means it makes lots of products really, really fast. So this reaction over here turns even more, take away my A's and B's maybe, it'll turn even more blue, whatever the blue might be. Because it's endothermic and it has to shift to the right. I think that covered that question. Let's see what other questions I might have. Oh, I think I'm back. Good. Okay. I have a few other questions. Just make sure I got. Here it goes. Gotta have an ice cream break. Okay, can you explain how you know the speed of the reaction? So what I'm covering is how can you explain how you know the speed of a reaction? That's a really good question. So if we go, oops, you can't see that. Push some better buttons here. Let you see this screen now. Okay. So if you go back to this part, if you look at a reaction A plus B makes, oh, that just looks funny. Let's try it again. A plus B makes AB. If you take a look at this reaction, the way I've drawn the arrows suggest that it's really reactant favored. It means you're going to have a lot of the reactants, which means my KEQ is going to be less than 1. I've got a lot of reactants. If I have a lot of reactants, that doesn't mean that the reaction happens slow. It doesn't mean it happened fast. KEQ tells you nothing about the speed of the reaction. Once again, KEQ can tell you nothing about the speed of the reaction. It only tells you what you have a lot or little of. So in this case, if this stuff is blue and this stuff is yellow, when you look at the beaker, what you're going to see is a lot of blue stuff, so your beaker would look blue. But that doesn't tell you much about the rate. The only thing that can tell you about rate is if you would actually make a diagram that looked at, over time, how much of the AB did you make. At the beginning of time, you don't have any AB, but over time, you might be making AB at this rate. I'm not really sure. And then a different reaction, maybe you're really making AB at this rate. Since the slope is really less, the red line shows a really slight slope, not a very steep slope. This is a slow rate because we're not making a lot of stuff over a long period of time. If we take a look at the green line, this is a faster rate because I am making a lot of AB in every given amount of time. So if I want to look at rate, I cannot look at KEQ. I can only look at actual graphs or look at numbers, which we didn't really look at. You could get the slope of the line, and that could tell you how steep it is. The steeper the line, the faster the rate. And that's the only thing that can tell you actually rate. Back to my screens. Okay, so can you explain how you know the speed of the reaction? That's how I know. Let's go back to my other questions. Oh, where did they go? Shoot, there's another one. Oh, can you explain transition state again? Yes, I can. Okay. What is transition state? Okay, so when I look at a reaction coordinate diagram, maybe this one. Oh man, that's a heck of one. We're looking at potential energy versus time. This one here has our reactants going to make our products, and our products are lower, which means that this is an exothermic chart. It shows us that we are releasing energy. The amount of activation we need goes from here to here. This is my activation energy. Now at the top of the hill, this is called a transition state. So if you have a reaction like HCl plus magnesium will make hydrogen gas and magnesium fluoride, that transition state isn't going to look like the reactants and it isn't going to look like the products. It's going to kind of look like in between. It'll just be a big mix of Mg, H's, and Cl's all in a clump. See, as the reactants, they're kind of HCl and magnesium separate. And as the products, they're hydrogen and MgCl2 separate. But in the transition state, which is what I'm trying to draw right here, they're just a big clump of everything together. So the transition state is just this in-between part. That's all I would say you have to know about transition state, other than the fact that transition state, if I ask you what energy it is, if this was at 50, it'd be 50 kilojoules. Transition state would be at 50 kilojoules. Saying this is 25 and this is 0. And my activation energy from this one would be the difference of this, or 25. And the amount of heat would be between these two parts. That would be the amount of heat released. I don't know, I'm going to say this is 5. It'd be about 20 kilojoules. Go back to my normal screen. Yep, okay. check my questions. I don't think I have any right now. That's a good question. You should get your own ice cream. Okay, this next question is, how does a reaction shift affect equilibrium? How does a reaction shift affect equilibrium? My sharing screen. Okay. Okay. So let's say you have this equilibrium. We'll say that it's blue on this side, and these things are green. According to the KEQ here, according to my arrows show that I've made a lot of products. That's why this arrow is bigger, which means my KEQ has to be greater than 1. It means I have a lot of products, which means it starts out green. Now let's say I do a stress to it. According to Le Chatelier's principle, you can stress out a reaction, which means you can add concentration, temperature, or pressure. In this case, I'm going to add concentration. So I'm going to add some more B. If I add some more B, suddenly this side is too heavy, and the reaction has to shift to make more ABs. It's suddenly going faster to the right. We are making more of those fast, which means at the moment I add AB, I'm no longer in equilibrium. It's all out of whack, because my KEQ is equal to AB, concentration, divided by A times B. So at the beginning of time, when I've got equilibrium, it's going to be greater than 1. Let's pick a number like 9. But once I add a lot of B, now I have this number that's super big, and it no longer equals 9 anymore. Well, I need to get it back to 9. The world has to go back to equilibrium. To make that happen, I've got to get rid of some of my B and make more of my AB. So that finally I can get new numbers in here, and I can remake my 9. So the whole point here is that it's in equilibrium. I'm going to add B, which stresses it out and suddenly makes it so this side is too heavy. It shifts to the right and makes more products really fast until it can remake equilibrium. Remake this KEQ of 9. Once it's back at equilibrium, then all the things, the rates are going forward and backward the same. It's just that moment that B is added that it's not exactly the same. And it's not in equilibrium anymore. All right. Let's go back to my screen. I answered all the questions I can see in my comment. I just refreshed it. Try my email. I'm having vanilla ice cream if you're curious. I have a question of how do you know if it's endothermic or exothermic? Okay. I'm assuming that this person may want to know maybe in accordance with the lab. So I'm actually going to really talk about the lab. Otherwise, on the test, I might say, you're saying, how do I know if it's endothermic or exothermic? I gotta get you on the screen. I know it's endothermic or exothermic most of the time on the test because I'm going to tell you. But for when I don't tell you, like in the lab today, if you think about what we had copper, 2 plus 4 fluorines, and they made this copper chloride compound. Okay, and I put them in these colors specifically because we know that this side was the green side and this side was the blue side. And I made my KEQ especially this way. You can see according to the arrows here that my KEQ is reactant favored, so the KEQ is going to be less than 1. And that makes sense because when I first got the solution, it looked really blue. It was blue when you poured the solution from the very start. Okay, so how do I know if it's endothermic or exothermic? What you saw today is when you added heat, because most of you heated it up, it tended to shift to the right and it made green stuff. It suddenly made green when you heated it. Now the stress that you applied was the heat. So if your stress was the heat, it was the thing that shifted it to the right. Now if it made it more green and shifted it to the right, that would mean this side was too heavy. The reactant side was too heavy. If the reactant side is too heavy, that's why it can shift to the right. The only way that this side could be too heavy is if we added heat to this side. Heat would be right here. So if I added heat, it would shift to the right like it did, and I saw green. And if heat is added as a reactant, then it's endothermic. So recap, it turned green because it shifted to the right. The only way it can shift to the right is if it's too heavy on the left side. If it's too heavy on the left side, that means heat had to be added to the left side. And heat added on the left side as a reactant is called endothermic. Hope that helped. Any questions there? Oh, question from Big Tom. How many questions are going to be? There's 20 multiple choice questions. There's 20 multiple choice questions, and there are 1 short answer. You're welcome to the people who don't like short answers. There's only 1 of them. I had 10 viewers and lots of good questions. Oh, my ice cream got melty. No, but thank you. Can I take this dish now?
You can call him Yeti.
I'm gonna end here soon. We got till 8:45. Hopefully I might get a few more questions otherwise. I'm gonna create a paper and okay. I like the questions. They're really good. Thank you. Thank you, folks. Okay. Oh, somebody did send me some chemistry funnies, some chemistry jokes. Thank you to that person. I'm going there now. Those are cartoony. Huh. Why do chemists like nitrates so much? Cheaper than day rates. Oh, this one's for Big Tom. I asked the guy sitting next to me if he had any sodium hypobromite. He said, nah, bro. Sodium hypobromate is NaBrO. Good one. What is the chemical formula for coffee? Cobalt iron 2, COFE2. It's a lot easier if you see it. Try and find a funnier one. Making bad chemistry jokes because all the good ones are gone. Are gone. If H2O is the formula for water, what is the formula for ice? H2O cubed. What do you call a tooth in a glass of water? 1 molar solution. Hello. These are terrible jokes. You're welcome. Apparently I have a spam section. Nobody has spammed me with questions. That's good. Well, to my 9 viewers out there, I gotta say that I'm going to stop in about, I don't know, 8:45, which gives me about 8 more minutes. So if you have a question, please let me know. Otherwise, it's been lovely being with you here today. I hope it was helpful. If it wasn't, well, you should just stop watching them. Big time, I got an email from Mrs. Farrow today. It wasn't about you, but I think she misses you. Okay. Thanks, Tom. I thought the jokes were good. Okay, the first question on the study guide. First question on the study guide is about if you have 0.010 molar or 0.005 molar, why would it slow it down? I'm going to go to my other screen here. That's okay. Yeah, that is right. There we go. Okay. So the question is from question number 1 on the review worksheet. And it was the idea if you have something that's 0.01 molar versus 0.005 molar. So what these molar big M mean is molarity. That means the amount of moles per liter. So this means that you have, that's not the thing I want. This means that you have 0.01 moles in every 1 liter. And this number means you have 0.005 moles in every 1 liter. So clearly this one has a higher concentration, is more concentrated, which means there are more particles inside, or more atoms, which means this one is colliding more often. And you have to have a collision in order for a reaction rate to happen, which means their rate is going to be faster. That is not looking pretty. Hopefully it worked. So in conclusion, to recap again, this top one has more moles of stuff. It's more concentrated, which means there's more atoms, which means they collide more often, which anytime you can collide more often means the rate's going to be faster. So the question is asking, why would it slow down when you have this molarity? Just the opposite. You have fewer stuff in the bucket, fewer collisions, it's going to be a slower rate. A capital M does mean molarity. The big M does mean molarity. If a reaction is product or reaction favored, does it affect the rate of the reaction? No. Product or reaction favored tells us about KEQ. Oh, I should click the button. Okay, let me try again. If the reaction is product or reaction favored, does it affect the rate of the reaction? It does not affect the rate of the reaction. Product or reaction favored is what KEQ tells us. So if KEQ is greater than 1, then it's product favored. We push it to the right a lot. If KEQ is less than 1, it's reactant favored. It means you have a lot of reactant at the beginning of time. But KEQ doesn't tell you the rate of the reaction at all. It only tells you which one we have more of, reactants or products. In order to know the rate of the reaction, you have to make a graph. Kind of like what we did in class when we did the bubbles counting. You'd have to see, or yours might have been when you looked at how fast it took for the bubbles to go away. We have to look at that versus time. And so you'd have to make a graph to know about the rate. And we we made graphs, but we didn't do numbers with it. So I hope that helped. I like this question. I know this is dumb. No, it's not. But what exactly is orientation? I asked Matty P earlier and he had no idea too. This is a good question. Okay. What do I have here that I could use? I don't know. I have crayons. Okay, orientation is just how it's moving in space. So if this crayon had to react with my calculator, they could hit in many different ways, but it has to be orientated correctly when it actually makes a reaction. So if these two things collide this way, the reaction will be effective. But if they happen to collide this way, it's not orientated right. And although they collide with each other, they're not orientated right, so they can't actually make a reaction happen. So not only do they have to hit in the right way. That's what orientation is. Thank you to that question. So does that kind of answer the last question on the lab? Oh, okay, to this person, this person was asking about KEQ. If you look at the very last question in the lab, in the very back of the lab, it says, I have a KEQ 4 point something. Is this faster or slower than the other one? And how do you know? Or something like that. It does answer the last question in the lab. The KEQ, no matter what the number, does not tell you the rate of the reaction. The KEQ does not tell you the rate of the reaction. So I think that should cover it there. On the study guide, under review number 2. On the study guide, under review number 2, it says to label the KEQ greater than or less than 1, but how do you know without numbers? Good question. I guess I gotta go to my other screen. Okay, so if we look at the review worksheet, under review worksheet number 2, number 1, it'll have equations like, it says 3Fe plus 4 waters. Oops. This. Okay, so here's my reaction, and the question is, how do we know what KEQ is, greater than or less than 1 or equal to 1? If you look at these arrows, they tell you your KEQ. We know it's in equilibrium because we have reversible reactions that go one way the arrow and the arrow the other way. So my KEQ, it shows that there's really big going this way. This arrow is so much bigger going to the right, which means I have a lot of these. And when we write KEQ, we write the products divided by the reactants. And in this case, if I happen to have a lot of these, that means my top number is really big, and a big number divided by any number is going to be a big number or greater than 1. So here, if my arrow points to the products, I have a lot of products, it'll be greater than 1. Greater than 1 means you have a lot of products. And the vice versa is true. If you happen to have a KEQ that is less than 1, then you're going to have a lot of reactants. And in that case, your arrow will look really big going right and a little bit going to the left, or vice versa. Really big going to the left and a little bit going to the right. And if your KEQ happens to be equal to 1, that means you've got the arrows that are the exact same size. For this one, try to do the same size. Question. Okay, this question is about the lab. And the question on the lab is asking, why didn't stress number 2 cause any stress in the system or shift the reaction? So if you think about stress number 2 was Na2SO4, and the question is, why didn't it cause a stress or a shift in the reaction? Okay, so we'll rewrite. It's copper plus 4 chlorines made bigger going this way. UCl14 minus. Okay, so I made it blue because the left side is blue and green because the right side is green. Yeah, so when we, stress number 2 in the lab was Na2SO4. In order for a stress to actually be a stress, it has to affect the equilibrium in some way. It has to mess with the reaction. Now, when you have Na2SO4, what you really have is NAs you're adding into the bucket and SO4s into the bucket. Kind of like if you have stress number 1, NaCl, you're really adding NAs and Cls to the bucket. For stress number 1, if I added Cl, I would add to this side, and that would make it too heavy, and that's why it shifted and make it more green. But if I've got Na2SO4, I got NAs. Na isn't anywhere in the reaction, and I look for SO4s. SO4s aren't anywhere in the reaction. And if it's not anywhere in the reaction, it really can't do anything in the reaction to mess it up, so it can't be a stress. So Na2SO4 didn't affect it because it's nowhere in the reaction. NaCl was, but Na2SO4 was not. Another question someone has is there an answer sheet to the review worksheet on Moodle? Yes, I did the review worksheet and the answer key should be on Moodle. I'm going to double check right now as you are watching. That way I know for sure. Make sure it's up there for that, folks. Yeah, it's at the very bottom. The review worksheet says Chapter 17 review worksheet, and then it says Chapter 17 review worksheet answers, right above the link that you did for this thing. Yeah, they're there. That's good. I'm checking on my question spots. And if there's no more, I think I might sign off. You all should go to bed and get some sleep. Okay, there's no question there. There's no questions there. So, yeah, that might be the end of the show. You guys kept me busy. I only graded 1 paper. That's not bad. I've gotten through a total of 3 of these papers thus far. It's slow going. I'm sorry, kiddos. Try to get on that. I give myself with these big of labs a 2-week deadline, so we're in the first week right now. To get on it. So if you have to get questions tomorrow, and you think of them tonight, I will check it in the morning and email you back with any questions you might have. And then I'll check it periodically throughout the day. And hopefully get back to you in time. I can't make any promises, but I will do my very best. Anyone, let's check the questions. And then sign off. Nothing there. Nothing there. I appreciate you coming and watching the show. To my 8 viewers that are currently with me right now, good night. Get some sleep. That's what I'm going to do soon. Okay, thanks.